Okay, let's unpack this. Um, Imagine a world where like every bit of info you send online just
Yeah.
floats out there, hoping for the best.
Chaos, right. Total chaos.
Exactly. Sounds chaotic.
Yeah.
Well, thankfully we have this unsung hero working behind the scenes, making sure emails arrive, videos stream okay, banking's secure.
Yep.
Today we're doing a deep dive into that hero, the Transmission Control Protocol, or TCP. You sent us this really fascinating stack of sources. It's basically a master class in core TCP stuff, the kind of thing you hear about in tech interviews, right?
Absolutely. Foundational concepts.
So our mission today is to pull out the most important nuggets of knowledge so you can really get what makes the internet tick, whether you're prepping for something, catching up, or just curious.
Should be some aha moments, hopefully.
Definitely aiming for that.
Okay.
Okay, so to kick us off, we always hear TCT, UDP. They're like cousins.
Right.
Right.
You could say that, yeah.
For someone who's heard the names but isn't like totally clear, what's the fundamental difference, the core thing listeners need to grasp? Maybe starting with that connection-oriented idea for TCP.
Right. Well, the simplest way to put it, it's reliability versus speed. TCP is kind of like sending a registered letter.
Okay.
You know it'll get there, you get confirmation. It's connection-oriented because it sets up a link, like a digital handshake, before any data actually moves.
Handshake first.
Exactly. And that handshake, plus sequence numbers, acknowledgements, retransmissions, it makes it incredibly reliable. Every packet is, accounted for.
Okay, so that's TCP, reliable. What about UDP then?
UDP is more like yelling across a crowded room. It's fast, yeah, but there's no guarantee anyone heard you or heard things in the right order. It's connectionless and, well, unreliable in that specific sense.
So if TCP is so reliable, which sounds, good,
Yeah.
why would anyone ever pick UDP, this unreliable option? When does that make sense?
Well, it's a classic engineering trade-off, isn't it?
Right.
See, TCP guarantees delivery, but that guarantee has overhead. All those handshakes, the ACKs, potential retransmits, they add latency, delay.
Ah, okay.
So for things happening in real time, like live video streaming or voice over IP calls, a tiny delay to resend a lost bit of data can be way more annoying than just dropping that tiny bit.
Right. You'd rather have a tiny glitch than everything freezing up.
Exactly. A momentary glitch over a frozen screen or a choppy conversation. So UDP goes for speed, low latency, perfect for that stuff. TCP, though, that's the workhorse for anything needing absolute accuracy. Web pages, file transfers, anything where every single byte has to arrive and arrive correctly.
Makes perfect sense. Reliability versus speed. Okay. Now, you mentioned the digital handshake a minute ago. This is where it gets really interesting for me.
Yeah.
How does a TCP connection actually start? It's not just, boom, they're talking, right?
Not at all. No, it's actually a very polite three-step process. We call it the three-way handshake.
3 steps. Okay.
Think of it like this. First, the client, the one starting things, sends a SYN packet. SYN is short for synchronize.
Okay, SYM.
It's basically saying, hello, server, I'd like to talk.
And the server responds.
Yep. The server replies with a SYN ACK packet. So it acknowledges the SYN and sends its own SYN back. It's saying, I hear you, and I'm also ready to talk.
SYN, ACK. So the third step must complete the circle.
Precisely. The client sends one final packet, an ACK packet, just acknowledge
Ah.
it. That finishes the handshake. Now, both sides know the other is ready, they've agreed on starting sequence numbers, and boom, reliable connection established. Only then does the actual data start flowing.
What's the real significance of setting it up so methodically? Why not just start sending data? Seems faster.
Well, beyond just stopping things being completely chaotic, the genius here is that it makes sure both sides are definitely ready and they agree on where to start counting the data, those sequence numbers.
The starting point.
Exactly. That initial sync is crucial for reliability, for order, for the whole conversation. Without it, how would you track what's been sent, what's been received? You'd get corruption, missing stuff. It's the quiet guarantee that your digital world, makes sense.
Okay, so handshake done. We're connected. Data's flowing. But how do they, talk? How do they manage that flow and keep everything in order? That's where these TCP flags and numbers come in.
Exactly. Flags are like little signals, little commands tucked into every packet.
We already heard SYN for starting things. And ACK is in the handshake too. What other key flags are driving the conversation once it's going?
Yeah, so SYN and ACK are crucial. For ongoing communication, definitely ACK is key, acknowledging received data. Then there's FIN. That's for finishing, terminating a connection gracefully when you're done talking.
FIN for finish. Makes sense.
Then you have RST, that's reset. It signals an abrupt stop, usually because something went wrong. An error, maybe?
Okay, so FIN is polite, RST is
Yeah.
not so polite.
Pretty much, yeah. There are a few others, like PSH for push, tells the application to deal with the data right away, and URG for urgent data, but yeah, ACK, FIN, and RST are the main ones managing the connection once it's live.
And alongside those flags, every chunk of data gets a number, you said.
That's right, two important numbers. The sequence number identifies the order of bytes being sent. Think of it like page numbers in a book.
Okay, page numbers.
And the acknowledgement number confirms which page has been successfully received. And critically, it tells the sender exactly which page number it expects next.
So it's not just got it's got it up to page 5, send page 6 now.
Precisely. These two, the sequence and acknowledgement numbers working with the flags, they are the absolute bedrock for data integrity and correct order.
So these numbers and flags are what stop, say, your online bank payment from happening twice by accident, or your video streaming totally out of sequence.
Absolutely. They're the invisible guardians, the silent orchestrators making sure complex things work on top of what's fundamentally, a somewhat unreliable network underneath. Without them, the internet we use every day, it just wouldn't work reliably.
That's fascinating. It really is. But okay, what if the network gets super busy? Or maybe the receiver just can't keep up with the sender? TCP is known for being adaptable, right? How does it handle that? There's flow control, I know that one.
Right, flow control. That's about preventing the sender from just overwhelming the receiver.
How does it work? Does the receiver just yell, stop?
Sort of. It's actually quite clever. The receiver uses a field in the TCP header called the window size field. It actively tells the sender how much buffer space it currently has available.
So it's like, hey, I've only got room for, say, 10 kilobytes right now. Don't send more than that yet.
Exactly like that. It dynamically adjusts. This stops data arriving faster than the receiver can handle it, which would just cause dropped packets and things needing to be resent.
Okay. And tied into that is the sliding window technique. I've heard that speeds things up a lot. How does that work?
Yeah, the sliding window is brilliant for throughput. So instead of the really slow method, send one packet, wait for the ACK, send the next packet, wait.
Yeah, that sounds painful.
Right. The sliding window lets the sender transmit multiple packets, a whole window's worth, before it needs to get an acknowledgement back.
So we can send packets 1, 2, 3, 4 before waiting for the ACK for packet 1.
Exactly. Maybe even more, depending on the window size. Imagine sending several pages of that book before needing confirmation. It massively boosts speed, especially on networks with a bit of delay, but still keeps all the reliability stuff TCP is famous for.
Makes sense. But it's not just about the two computers talking, right? TCP also tries to be a good citizen on the whole network with congestion control. Yeah. Stopping the entire internet from grinding to a halt. What's the idea there?
Yeah, this is where TCP gets really, really sophisticated. It uses a whole set of algorithms. You might hear names like slow start, congestion avoidance, fast retransmit, fast recovery.
Okay, fancy names. But what do they do?
Basically, they're the internet's way of feeling out the traffic conditions. TCP starts sending slowly, then ramps up. If it detects signs of congestion, like packets getting dropped or delayed, it backs off automatically. It slows down. Then it carefully tries to speed up again, testing the waters.
So it's constantly adjusting its speed based on how busy the network seems.
Constantly. It's trying to find the sweet spot send as fast as possible without causing a network traffic jam.
And of course, if a packet does get lost, despite all this, TCP has that safety net, retransmission.
Absolutely fundamental. If the sender doesn't get an ACK back for a packet within a certain time, a timeout period,
It just sends it again.
it just resends that specific missing packet. Or another clever trick, if it receives the same ACK 3 times in a row for an earlier packet, we call those triple duplicate ACKs, that's a strong signal the next packet got lost. So it resends the missing one immediately, often without even waiting for the full timeout.
Wow.
It guarantees delivery even when the network itself isn't perfect.
It really is incredible. Just thinking about the millions, billions of tiny, invisible decisions TCP makes every single second. Just to get, I don't know, my cat video from some server to my screen.
It truly is the unsung hero, like you said.
Okay, let's dive into 2 more kind of subtle but clever optimizations TCP uses. Improving efficiency. First up, Nagel's algorithm. What's that one about?
Ah, Nagels. Right. That's all about reducing the number of really small packets flying around.
Yeah.
We sometimes call them tiny grams.
Tiny grams. Okay. Why are they bad?
Well, every packet has overhead headers and stuff. Sending lots of tiny packets, like maybe one for every single keystroke in a remote login session,
Yeah.
is pretty inefficient. Nagel's algorithm says, basically, hold on a sec. It waits for either a decent chunk of data to collect or for an ACK of the previous packet to come back before sending the next small bit. It bundles them up.
So it combines small outgoing messages into one bigger, more efficient packet.
Exactly. Reduces overhead, reduces potential network congestion, makes things smoother, especially for interactive stuff.
Okay. And then there's TCP delayed acknowledgement. Now, delayed sounds like it might slow things down, but you're saying it's an optimization.
It is, counterintuitively, perhaps. It's a technique where the receiver deliberately holds back on sending an ACK immediately, just for a very short time, maybe up to 200 milliseconds, or until it happens to have some data of its own to send back.
Why delay?
The hope is either to bundle the ACK with some outgoing data piggybacking it, or to acknowledge several received packets with just a single ACK packet, instead of sending an ACK for every single one.
Ah, I see. So it reduces the total number of ACK packets, which are also overhead.
Precisely. Fewer small ACK packets floating around saves bandwidth, saves a bit of processing power on both ends. It's another efficiency gain.
So these things, Nagel and delayed ACK, they seem like tiny details, but they actually add up. They help make the network less chatty, more efficient, improving responsiveness for you, the user, without you even noticing.
Exactly. Optimizing the background chatter to make the main conversation smoother.
Right. Now let's switch gears slightly. How does my computer, when it's got like 10 browser tabs open, email running, maybe a download, how does it know which incoming data belongs to which specific conversation? And how big should those data chunks be? This involves something called a TCP socket.
That's the key. A TCP socket is what uniquely identifies each end of a specific connection. It's not just the IP address of the computer.
No.
No, it's a combination. The IP address, a specific port number, and the protocol being used. So an example might be 10.1.1.1.5.443 TCP. That tells you it's a TCP connection going to IP address 10.11.5, specifically to port 443, which we know is usually HTTPS.
So that IP plus port combo is the unique address for that specific connection.
For that endpoint of the connection, yes. The combination on both the client and server uniquely defines that entire conversation, allowing your computer to juggle many at once.
Okay. And when setting up connections, I read about active open versus passive open. What's the difference there?
It's basically client versus server. The client usually performs an active open. It's the one initiating the connection, typically using a command or function like connect. It's actively reaching out.
And the server?
The server does a passive open. It sets itself up to listen for incoming connections on a specific port using a function like listen. It's passively waiting for someone else, a client, to initiate.
Got it. Active client, passive server. Now, packet size. There's MSS, maximum segment size. What does that control?
Right, MSS. That's the largest chunk of actual data. So, payload, not including the TCP headers that one end of the connection is willing to receive in a single TCP segment.
So it's like saying, don't send me pieces bigger than this much.
Exactly. And critically, this is usually negotiated during that initial three-way handshake. Both sides tell each other their MSS.
Okay, and this relates somehow to MTU, maximum transmission unit. That sounds similar.
It's related but different. MTU is a lower-level concept, usually at the network interface or link layer. It's the largest total packet size, including all headers, that a specific network path can handle without breaking the packet up.
Breaking it up. Fragmentation.
Exactly, fragmentation, which is generally inefficient and something you want to avoid if possible. So TCP is clever. It learns the MTU of the path, or at least the MTU of its local network interface, and it adjusts its MS downwards if necessary.
So it makes sure its segments plus the TCP IP headers won't exceed the network's MTU limit.
Precisely. It tries to avoid forcing the lower network layers to fragment the packets. It's all about coordination between the layers to ensure smooth, efficient delivery.
Wow. Okay, the level of invisible negotiation and agreement just to get data flowing. It's pretty mind-blowing when you stop to think about it. These things, MSS, MTU, sockets, they sound abstract, but they are absolutely vital for making sure everything talks correctly online.
Couldn't have said it better myself. They underpin those seamless digital interactions we take for granted.
Okay, so connections get established, data flows, but connections aren't always perfect and they don't last forever, right? How does TCP handle things like long silences or closing down properly? Let's talk about TCP Keep Alive. What's that for?
Keep Alive is basically a checkup mechanism. If a connection has been completely silent, no data flowing for a long time,
Yeah.
one side might send a small Keep Alive packet. It doesn't contain any real data, it's just a probe. If it gets an acknowledgement back, it knows the connection is still alive and the other end is still there.
And if it doesn't get a response?
After a few tries, it assumes the connection is dead and cleans it up, freeing up resources. It stops connections from just hanging open forever if, say, the other computer crashed or the network path broke silently.
Right, prevents zombie connections.
Yeah.
What about a half-open TCP connection? That sounds...
Bad. It can be problematic, yeah. A half-open connection happens when one side, say the client, crashes or resets the connection abruptly, but the other side, the server, maybe doesn't find out immediately.
So the server thinks the connection's still open.
Exactly. It keeps resources allocated in memory, maybe a process slot for a connection that isn't actually functional anymore. If you get a lot of these, it can lead to resource exhaustion on the server, timeouts, application errors. It's something network administrators watch out for.
And after a connection closes normally, it doesn't just vanish instantly, does it? There's this thing called the time wait state. Why does that exist?
Time wait. That's crucial for robustness. So after the side that initiates the close sends its final ACK, it doesn't immediately forget the connection. It hangs around in this time wait state for a specific period.
How long?
Usually it's defined as 2 times the MSL, the maximum segment lifetime.
MSL, maximum segment lifetime.
Yeah, that's sort of the theoretical maximum time a packet could possibly wander around the internet before being discarded. So, waiting for twice that long gives any stray, delayed packets from the old connection plenty of time to arrive and be discarded, ensuring they don't accidentally get delivered to a new connection that happens to reuse the same port numbers later on.
Okay. So it prevents old, late data from messing up a brand new conversation.
Exactly. It's a safety mechanism.
And just to circle back the flags quickly, we mentioned FIN for a graceful close and RST for an abrupt one. Can you just recap the key difference in how they terminate things?
Sure. FIN is the polite way. It's a two-way shutdown. One side sends a FIN saying, I'm done sending. The other side acknowledges it, finishes sending its own data, then sends its own FIN. Then the first side acknowledges that. It's a complete, orderly close.
Like hanging up after saying goodbye properly.
Exactly. RST, reset, is like slamming the phone down. It means something's wrong or I'm aborting this connection now. There's no waiting, no further acknowledgments needed usually. It just kills the connection immediately. Often seen when there's an error or if one side tries to send data to a connection that the other side doesn't recognize anymore.
Got it. Polite FIN, abrupt RST. Now, what about TCP handling packet loss? How does it smartly recover when a packet just goes missing in the network?
Well, as we touched on, it relies heavily on those sequence numbers and acknowledgments.
Yeah.
It knows which packet should come next. If it doesn't get an ACK for a sent packet within a reasonable time, like the timeout,
It resends it.
it resends it.
Yeah.
Or if it gets those triple duplicate ACKs, meaning the receiver is saying, I got packet 5 3 times, that's a huge hint that packet 6 is missing. So TCP will often resend packet 6 right away, even before the timer expires. It's very resilient to occasional network hiccups.
Makes sense. And just for folks listening, maybe wondering what common services rely on this. What are some typical TCP ports and applications they might encounter?
Oh, loads of common ones. Port 80 is HTTP, standard web browsing. Port 443 is HTTPS, the secure version.
Right.
Port 22 is SSH for secure remote logins. Port 25 is SMTP for sending email. Ports 20 and 21 are traditionally used by FTP for file transfers. Those are probably the biggest ones people interact with daily, even indirectly.
And if you do suspect a TCP issue, maybe a connection problem,
Mm-hmm.
are there any quick troubleshooting commands people can use?
Yeah, definitely. On Linux systems, commands like netstat-nt or the newer SST are great. They show you active TCP connections, their states, which ports are being used. TCP dump is more advanced, lets you actually capture and see the packets, like TCP dump port 80 to see web traffic.
And for Windows users?
On Windows, netstat-n is the classic command. It gives similar info lists, connections, ports, states. Just knowing these basic tools can be incredibly helpful if you're trying to figure out why something isn't connecting properly.
You know, it reminds me, I once spent hours debugging a server problem. Turned out it was simply running out of available ports because way too many old connections were stuck lingering in that time wait state we talked about.
Yes, a classic issue.
It sounds like such a minor detail, right? But understanding these connection lifecycle states, the flags, how things close, that's often where the real-world network gremlins hide. Knowing this stuff can genuinely turn you from just a frustrated user into someone who can actually figure out what's going on.
That's a perfect example. These concepts seem abstract until you hit a real problem, and then suddenly understanding time weight or how RST works becomes very, very concrete and useful. It's the difference between guessing and diagnosing.
So wrapping this up, what does this all mean? We've taken a pretty deep dive here into TCP. It's this invisible, incredibly reliable backbone for almost everything we do online.
It really is.
It's the protocol making sure your data gets from A to B, completely in the right order, pretty much every single time. And why should you, listening, care about all these intricate details, these flags, handshakes, windows? Because understanding these fundamental layers, it gives you real insight into how our connected world actually works, into reliability, speed, security, all the things we depend on.
It demystifies the magic a bit.
Exactly. So next time you click a link or you send an email or stream a video, maybe take a second to consider that intricate, invisible dance happening underneath. All these TCP mechanisms working together. How might understanding this silent orchestrator of the internet change the way you think about digital reliability or even security in your day-to-day online life?